So let's start the class. So to remember, the final is the first day. The first day, right? So don't forget the first day. Not next Thursday, but the following Thursday. Okay, so don't forget for the final, you can print out the equation sheet plus remember the last page of 3.1, 3.2, and 3.3. Okay, you can do that. I will have extra equation sheet, but I'm not sure if those are very helpful, so I recommend instead to print out those last pages, right? What else? So 12 to 2. It's from 12 to 2. Okay, so don't forget in person on paper. And because it's the first day, it will be very, very hard to have a makeup because some people are graduating. So I have to go fast, grading everyone. So make sure you make it. Okay, please, 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 please make it. I have, yes. 20, about 20 or 21. 20 questions about. And I have uploaded the practice exam. And in the practice exam, so the practice exam does not count, but in the head of the practice exam, I'm telling you which questions to expect that is not in the practice exam. Okay, and I have you have an assignment for next week. You have an assignment for next week. And pay attention to the pop quiz of today. Okay, so let's start the class. So first of all, a student in my other classes, we were talking about, AC, alternating voltage, alternating current that we get from the outlet. And what's the frequency from the outlet? So 120 volt AC is the RMS, but the frequency 60 hertz, right? 60 hertz. So I told you that the light is blinking, okay, at a frequency of 60 hertz, but you cannot see it with your eyes because of your eyes. It will take time to refresh. Okay, it doesn't refresh very quickly. So what he did this morning, he took a video of the sign, and you can see it. You can see it flickering. Yeah, I think you have to slow down the video. Isn't that awesome? So if you compute how many times on off on off on off, it should be 60 times a second. But you cannot see it with your eyes because our eyes, takes time to refresh. Okay, it's like our software, or maybe it takes time for information to go from your eyes to your brain or whatever, how it works. But I thought that this was very cool. Isn't that very cool? Right? And another thing that I have found here that was from Long Island, the eclipse, and you see the moon. Huh? Isn't that cool? So you have some twinkling, because that's the atmosphere between the sun and the earth. I mean, the atmosphere of the earth, but otherwise super cool, extra cool. Okay, I did see it in Miami, but not, of course, it was just a little bit of it. Isn't that cool? So the whole eclipse only lasts for 7 minutes, so it doesn't last very long. And that was from a student, I forgot who. So in Miami, that's what she was able. It's not none of you. I forgot who sent me this, but you can see here you are missing part of the sun. Isn't that cool? So that's a picture, high resolution by NASA. So it's much better. And you see the moon here, just blocking the sun. How cool is that? And you can see here the corona. Okay, and you can use simple geometry to understand why is that it can totally block the sun, right? So if you remember from high school or middle school, it's called a similar triangle, right? So it just happened. So this is the moon here, and this is the sun. It's just happened that distance So the size, that size here, as seen from here, the size of the sun is 400 times larger than the size of the moon. Okay, and it just happened that the ratio between distance Earth moon and the Earth sun is also multiplied by 400. So remember from middle school, big base is to small base what big height is to small height. So that's how it happens. That's how the moon can totally block the sun, because it just happened that you have this ratio between the size and the distance. Isn't that crazy? It's like someone, is really designing the universe to make it work using very simple math equations. Okay, and I wanted to go back to the video, so I want to make sure sometimes I go too fast, and I want to make sure I didn't say something wrong. Remember the Veritasium video? No, you don't? Okay. Okay, so now I'm only using his expression. Okay, no, you can't.
I like to think of Lenz's law as the no you don't law.
So in that case, here you have a magnet, a very strong magnet. So the only way to have a very strong magnet is to have an electromagnet, right? And possibly to cool it down, okay? So at low temperature, so the current can flow, so you can have more current. By controlling the current, you control the magnetic field. That's the idea of an electromagnet. You don't need to connect it to AC power supply. You could if you want, but if the conductor is moving relative to the magnet, then you have current that will be induced, right? But if you see levitation, so then yes, the electromagnet here will be connected to AC power supply, because that way the magnetic field will expand, collapse, expand, collapse, expand. So the magnetic flux will change, okay, through the copper plate or aluminum plate, and it will induce eddy current, okay? So probably it's a AC power supply after all, because I think even if it doesn't move it, it's
Because
levitating.
whatever you try to do,
No?
nature acts to oppose you.
There you go.
If the plate is falling, eddy currents are induced to slow its descent.
Oh yeah. It's levitating, so it must
But
be
if
a
you try
power
to pick up the
supply.
plate,
AC power supply. Okay, so that means you can just induce current just with a permanent magnet, as long as the conductor is moving relative to the magnet, or you can move the magnet relative to the conductor, or you can have, for example, an electromagnet. Okay, the conductor here is not moving, electromagnet with AC power supply, that will work too, but something has to change. Okay, and another thing I wanted to show you from last time, that will be so AC power supply. So the power supply we get from the outlet. Okay, you can see what's happening here. That will be the hot, that will be the return path, then that will be the hot, that will be return path. So you see how it's switching on back and forth, switching back and forth 60 times a second. You see that, the outlet? Okay, so this hole will be plus, and then it will be return path, and then it will be hot, and then it will be return path, and then it will be hot, and so forth and so on. So it's going to switch, okay, 60 times a second. That's why we have 60 hertz. So the AC power supply, okay, we're going to get AC current and AC voltage, and it will follow a sine wave. The peak voltage is 170, the RMS is 120. Okay, is that clear? Okay, cool. Okay, what else? Just to make sure you get the pop quiz right for today. You see, this is the electromagnetic spectrum. So I might want to trick you, and I try to convince you that gamma rays will go faster than radio waves, because gamma rays, of course, going to carry more energy than radio waves. Is that true? No, right? All of them, all of them will have a single speed. That will be the speed of light. Okay? Even though they do not have the same wavelength, even though they don't have the same frequency, okay, they are still electromagnetic waves, and they all travel with the same speed, the speed of light. Okay. Second thing, I will try to trick you, maybe for the pop quiz. You see the visible part of the electromagnetic spectrum, the part that you can see, you can sense with your eyes, will be very, very, very small. Okay, so the visible part is a very, very small range of the whole electromagnetic spectrum. So most of the electromagnetic spectrum is invisible for us. So you have to build special sensors or special telescopes to be able to detect infrared. You need to have antenna to detect radio waves. You need to have special sensors for X-rays or gamma rays, right? But our eyes can't. So if I ask you what's most of the part of the electromagnetic spectrum, it's going to be invisible. And then you have to know the order. Okay, so if I ask you for the final, it goes from gamma rays will be the smaller wavelength, larger frequency. So you see the frequency is 10 to the 24. So 100000000000000000000. So high frequency. So if I was able to take, for example, a magnet in my hand and I can shake it that fast, impossible. But if I was able to do it, I will emit gamma rays. Okay, so the frequency is very high, and we're going to see that gamma rays are so small that they will behave more like particles, like projectiles, little bullets, little projectiles that we're going to call photons, right? So when gamma rays goes through your body, okay, they will be so small, okay, smaller than the nucleus, okay, smaller than the atoms that make you inside you. So it will destroy the cells, right? So gamma rays going through you will burp out its energy. Each photon will burp out its energy in the cell, okay, biological cells, and destroy. And you have what it's called gamma ray knife, that you can use gamma ray to destroy your tumor, but at the same time you are also destroying healthy cells. So you are just hoping that you are destroying more cancer cells, that you are destroying healthy cells. But of course you can also destroy healthy cells, like it's the same idea for chemotherapy, right? Chemotherapy, you are just hoping that you kill more cancer cells than healthy cells. So anyway, so when the wavelength goes down, the frequency goes up. That's because the speed of light equals wavelength times frequency. So wavelength and frequency are inversely proportional to each other. Got that? Okay, so then you go to X-ray. Okay, all that is bad. UV, not so good. Visible, totally fine. Infrared, that will be heat wave. Okay, so longer wavelength. Microwave will be in the millimeters, and radio waves and long radio waves. Okay, what else did I forget to tell you? So you have to memorize the order. Okay, the other thing that you have to remember is that each time a charged particle oscillate, okay, then you're going to create an electromagnetic wave, okay, or a magnet. So if I take a magnet and I shake it, okay, so it's going to oscillate, okay, that will be the source for an electromagnetic wave. But of course, I don't shake it very fast, so you're going to make a very long radio wave. Okay, if you have an antenna, you are broadcasting something. Okay, so you have an antenna here. These are electrons shaking. Okay, so the source for electromagnetic waves are oscillating charge. Okay, so each time a charge is oscillating, it's going to create radiation, electromagnetic waves. So I don't know if you remember, the Earth, okay, has a magnetic field to protect us against charged particles coming from space. And then those charged particles, they're going to be trapped around the field lines. Remember that? They're going to spiral around. So when they go around, that means they do have an acceleration, okay? They have a centripetal acceleration. So they're going to radiate. They're going to emit light. That's the idea of the Van Allen belt, right? So each time a particle is accelerating, a charged particle is accelerating, either it's going around or it's going up and down, it's going to emit radio waves. Yes, yes. No, no, very good. Yes, right? Neutron, no. Electrons. Electrons do, or any charged particles that you shake, okay, is going to emit radio wave. So that's how we can make a signal. We have an antenna. Okay, that was this one here. Yes. If you shake them, or if they go around, they're gonna emit light. Okay, so for example here, I'm gonna oscillate the electrons. So I'm broadcasting here. Okay, so maybe I'm recording a song. The electron here, so you have an electronics electronic circuitry. So the electron here is oscillating up and down in the antenna. So you see an electric field is being produced. It's going to propagate in space. So as it's moving away from the source, it's going to lose energy because the energy will spread out in space. And at the other end here, the electric field is going to pull and push on that electron, and I will have a signal, and then you have some electronic circuitry, and that will turn that into a voice. So that's how it works. It's more like in 3 dimensions. That works like this. Okay. Let's see if I have. Okay, so the other thing I want to make sure you have to use your very educated beaver. So if C, so the velocity is this way, when the electric field is up, the magnetic field is towards you. Very educated beaver. You see that the electric field and the magnetic field are always perpendicular to each other, and they are in phase, which means when the electric field is maximum, the magnetic field is also maximum. So an electromagnetic wave, okay, has two components: shaking electric field, shaking magnetic field, or oscillating electric field, oscillating magnetic field. So if I take a picture at a given time, okay, you take your camera, you take a picture, you see the distance here, crest to crest, is going to be the wavelength. And now if instead I stay here at that point, you see it's going to go up and down and up and down. The time it takes, it's going to be the period. Okay, so that will be the antenna here. And you see how the electron that is oscillating is producing an electromagnetic waves in space. Okay, so at a given point, the electric field is going to go up, 0, down, 0, up. And the magnetic field at a given point is doing the same thing. 0, maximum, 0, minimum, 0. Okay, so they are oscillating in phase. meaning at a given time, if the electric field is a maximum, the magnetic field is also a maximum. And then here I fix my slide. So very educated beaver. So if E is down, B is in the board. And then you go here, very educated beaver. V is to the right, E is up, B is in the board. Is that clear? So an electromagnetic wave, okay, is like any wave. It will carry energy in space. So it's a disturbance that is moving in space at the speed of light. Yes.
Could you put that point where you said when the electromagnetic, what was it, the wave or the field is at maximum, then something else is also maximum?
So if the electric field here is maximum, B is also maximum. So that means they are in phase. So I think I show you a video. I like here, let's see this one.
Of oscillate light beam and to the electric field.
Here, you can see that here. You see here, I don't know which one is what. Okay, it says the electric field is down, the magnetic field here is there. So they are both perpendicular to the direction of propagation. But what you should see here, look at that point here. Look at this point there. You're going to see that the electric field goes to a maximum at the same time that the magnetic field gets to a maximum. So that will be magnetic field, electric field. So let's see. They are in phase. Look.
Both fields are in phase.
Big,
This means that if we focus on a specific point of the beam, they reach their maxima at the same time and cancel at the same time. The more intense the beam, the greater the amplitude of both fields.
Does that make sense? So they oscillate, okay, at the same time. When one is maximum, the other one is also maximum, okay? You can see that here.
Reach their maxima at the same time and cancel at the same time.
Field, blue is
the more intense the beam, the greater the amplitude
field.
of both fields.
So they are in phase. Okay, does that answer your question? Okay, so let's go back also to wave. So here it's a water wave. So you have a source and you see the wave is moving at a given speed. That speed is always, okay, the wavelength times the frequency. But if you move very far away from the source and you are looking here, okay, for that much distance here, you see that the waves are almost parallel to each other. So they are almost what we call plane wave. So it means if I take a small plane like this in this direction, okay, so if I put a plane in this direction perpendicular to the screen, all those points here will have exactly the same amplitude. So these are called plane wave. Okay, when you are close to the source, these are circular wave. Okay, so this is in 2 dimensions. So this is a crest, a throw, a crest. The distance between 2 crests is the wavelength. And again, if you stay at a given point, you see go up, down, up, down, up, down. The time it takes to go up, down, up is the period. During that time, the wave has moved one wavelength. That's why the speed will be equals to the wavelength divided by the period. Okay, so it takes one period for the wave to move over a wavelength. Is that clear? And then the experiment, so I insist because MCAT, I think they love two-slit. The two-slit experiment is very famous here. So you have 2 sources, okay? And from the sources, you have exactly the same frequency, the same wavelength. And you see sometimes the waves interact with each other but constructively, and sometimes they destroy each other, right? So it's called interference. So sometimes you have a crest and a throw. So here it's going to be flat, and here it's going to be flat. Sometimes they reinforce each other. So you're going to have twice the amplitude, okay, or twice the throw. Okay, so we already talked about that. But Thomas Young, experiment 1801, did the same thing with light. Okay, so that's why it's called a two-slit experiment. So it works only with, you need to have the same wavelength here. Okay, and if you take a screen here, that's what you're going to get. So the light cancel each other. Isn't that amazing? You have light from here, light on there, and they cancel each other. So here it's going to be dark, black. Here they will reinforce each other, crest to crest, throw to throw. So you have a bright spot, fringe. Isn't that interesting? Right? So this is called interference. Okay, you can change also the wavelength. Okay, so that will be the pattern for a smaller wavelength. Okay, still dark, bright, dark, bright, dark. And then once you understand the concept, everything else is just algebra. Okay, so if you have that for the MCAT, for example, there is a unit about that. But once you understand here, it's just math. The most important thing is to understand. Okay, another property for waves, and it doesn't have to be just light, but it's also true for any wave, is that waves always want to bend over corners, right? They will spread out. So this is called diffraction. Okay, so it means a wave wants to bend around corner. So it means here you have a small opening. So that small opening could be the opening of your eyes. It could be the opening of a telescope, or it could be the opening of a microscope. So what does matter for a microscope? Is it magnification or is it resolution? Resolution, very good, because if you have a small fuzzy thing and you make it a big fuzzy thing, it doesn't really help, right? So it's not magnification. So sometimes you buy a crap, and it says, oh, magnification is times 100. It's just a scheme. It doesn't really help. Small fuzzy, big fuzzy, it's not helping you. You want a good resolution. So why do you have issues with resolution? It's because of something we call diffraction. Wave, like light, will bend around corner. So you see here, light goes through an opening. So it could be a microscope, or it could be a telescope, or it could be your eyes, or it could be sensors. Once it's go through that opening here, instead of having just a dot, it's going to spread out. Okay? If the wavelength is very small, okay, like blue light, it's like it doesn't feel the corner. You say, okay, I'm fine. I don't feel anything here. Okay, I'm going to go straight. But if you have a large wave, like a radio wave, okay, and you try to collect that radio wave with a telescope, it's like, ooh, there's a corner. Ooh, there's a corner here. So it's going to spread around the corner, right? So that's why you always get a better resolution if you use blue light rather of using red light, for example. So why is it that for biology you want to use an electron microscope? Because electrons behave like waves, but they have a very, very small wavelength. So it means a very good resolution, okay? So this is called diffraction. So I have like from my astronomy class, you can see here, if you have two stars, okay, or maybe you are looking through a microscope at two bacteria, okay, you're looking through that opening of the microscope, so that will be a lens. If you have a good resolution, then you can tell the two bacteria apart. But if you do not have a good resolution, both here, the light coming from that bacteria and the light coming from that bacteria is going to spread, okay? Spread around the corner and they will merge together. And then you do not have a good resolution, okay? And you cannot see very small things. Same thing with your eyes. When the car, for example, is very close, you can tell apart the headlight, but if it's very far, you get a bad resolution and it's merging together. Do you understand? So with light, for example, if you are using blue light, it's better than if you are using red light. So the principle in biology is that to see something, if you are looking at something, I don't know, DNA, whatever, bacteria, hair, you need to use a light with a wavelength smaller than what you are looking at. Okay, so if you are looking at hair will be thicker than visible light. So you can use visible light, you can use a regular telescope, but you are trying to look at a virus. I don't know, virus is 0.7 micrometer. So you need to use a light with a wavelength smaller than that. So I don't know if you can see, I don't think you can see a virus with a regular microscope, right? So that's the idea. So you cannot use light that has a wavelength larger than whatever you are looking at. This is because of diffraction. So diffraction happens not only for light, you see, now if I use blue light, smaller wavelength, you don't have that much diffraction. If I use red light, it has a large wavelength, so it's going to diffract more. Does it make sense? Because it's so large that it's going to fill the openings. Ooh, opening here. Ooh, opening. I'm going to spread out. If you are using electron waves, okay, like an electron microscope, you know, those who are very, very expensive, the electron have such a small wavelength, it's not going to fill the opening, so it goes straight. And you have a very good resolution. Okay, so the idea of diffraction also happen for wave, right? Not wave, I meant water. So if I have water, I just want one slit. Okay, so if you just have one opening, do you see how it's spread out? Okay, so that wavelength here is about the size of this opening. So it's going to fill the openings. Ooh, there is an opening. Let's spread out. Okay, I can feel the corner. Okay, I'm not going to go in a straight line. I'm going to spread out. Of course, if you increase the size of the opening, I don't know if I can do that, like this, it doesn't spread that much. Okay, smaller is the wavelength or larger is the opening, less spreading out do I get. Okay, so that's, you don't have to worry about that for the final, that's just for the MCAT people. I have a playlist where I go over optics, but once you understand the concept, it's easy. Okay, let's go back to our business here. So I talk about diffraction. That's my other class. Okay, so I talk about that. Okay, let's move on. So we did that. Okay, so electromagnetic waves carry energy. That you know, because if you go, for example, outside, your skin can burn. Okay, so that means that it comes from energy. So that means that electromagnetic waves do carry energy. You can see that also if you are using a microwave oven. Okay, the electric field here, which is part of the microwaves, will pull and push or will twist the water molecule because it's polarized, right? So the electric field will push one way and then push the other way and then push one way, push the other way. Okay, so there is energy and that will warm up your food. Okay, so we already talked about that. Now, if you remember when you have a capacitor, the energy was stored inside the electric field, right? So you charge a defibrillator, okay? So you are using energy from your power supply. There is work done by the power supply on the defibrillator, okay? So it takes time for the defibrillator to charge. All that energy that you are draining from the power supply goes into the electric field. So you are storing energy inside your electric field. And then you go across the heart, you discharge inside your heart, and all that energy is being burped into a surge in current, and you are trying to make your heart pump again. Do you agree? Now, remember a solenoid, okay, a coil, okay, an electromagnet work exactly the same way. You are storing energy, but instead of storing energy into the electric field, you are storing energy in the magnetic field. Okay, so remember how we talked about an electromagnet, for example, when you connect your solenoid, your coil to a power supply, it's going to take time for the magnetic field to expand. Okay, how much magnetic field you're going to get depends on the geometry of your solenoid, right? So it's going to take time, okay, and it's going to drain energy from the power supply. Where that energy go? Into the magnetic field. Very good. Okay, so an electric field or a magnetic field are storehouses for energy. Okay, so remember when you are starting your car, you are using what is called a plug, okay, a starter plug. That's because all that energy that you took from the battery was stored inside the coil, ignition coil, and that ignition coil is going to burp out its energy as a voltage. It will make a spark that will start to burn the gas. Okay, so you do have energy in the magnetic field. So guess what? Let me ask you something. Okay, if you follow along, so don't fall asleep. Okay, how come the electromagnetic wave carries energy? Where is the energy? Inside the wave, but where? Inside the electric field, but also inside the magnetic field, exactly where the energy is stored. It's stored inside the electric field and the magnetic field, and it's moving, okay, until it finds a way to burp out its energy. Okay, it's like like a microwave, right? It uses the energy to twist the water molecules. So electric field will store energy, magnetic field will store energy. And because favoritism is not appropriate, okay? So we don't want to have jealousy. We don't want to make favoritism. So half of the energy will be inside the electric field and half of the energy will be inside the magnetic field. So no one is jealous, right? Half of the energy inside the electric field, half of the energy inside the magnetic field. So an electromagnetic wave, okay, it's like radiation, and radiation is just a flux of energy flowing in space. Flux of energy, okay? So for example, if you have an infrared lamp, okay, you can feel the heat on your skin, right? So all that energy, okay, locked inside the radiation, infrared radiation, is going to spread in space, okay, and you're going to feel that energy when those radiation are going to touch your skin, okay, your skin is going to heat up. Okay, so all that energy is being burnt out inside your skin. Maybe it's going to excite the electrons of your skin or the molecules of your skin, and that's why your skin gets hot, right? Okay, so that's the meaning. So physics is not that hard for, at least for biology and taking the MCAT. most important, my advice is to understand the concept. Once you understand the concept, everything else is just algebra. Okay, so we're going to write it this way. We're going to define the density, okay, energy density, meaning the energy per unit volume. Half of it will be inside the electric field, half of it will be inside the magnetic field. Okay? And so I'm doing acupuncture those days. I'm trying. Okay, so what she does is she always has a heat lamp. Okay, so you have radiation here, so it's heat up the skin. My point is that you can imagine here, okay, you take 1 unit volume. So that means a volume 1 meter by 1 meter by 1 meter. How much energy, okay, is inside that 1 unit volume? That will be equals to that. Okay, so unit density, energy density, okay, that's what it means. How much energy will be in a unit volume? Is that clear? Half of it inside the electric field, half of it inside the magnetic field. Okay, I like this example because you all have experience heating lamp, especially if you have a reptile. Someone has a reptile? No?
Is the constant 8.9?
Yeah, so let's go back to that. Yes. Yeah.
So will energy always be half in the electric project?
Yes, always. Half and half. So half and half. Okay? Second of all, mu sub 0 is the magnetic constant, so it's 4 pi times 10 to the negative 7, and then it has some unit here. Epsilon 0, that's what we used for static electricity, and it was 8.85 times 10 to the negative 12 something. So this part here and this part here are equal to each other. Okay? 1/2 inside the electric field, 1/2 inside the magnetic field. And we are talking about the energy density. So again, you take 1 volume equals to 1. Okay, so 1 meter cube. And let's say you have a infrared lamp. So you have radiation traveling, okay, in space. And that will be giving you how much energy can be found inside that volume here. Okay, so once you visualize, it's easier to understand. Is that clear? In addition to that, so you know that those terms has to be equals to each other. So 1/2 epsilon, I'm losing my voice, b squared. So you see they have to be equal to each other because it's going to be the same energy. In addition to that, remember the speed of light equals to this. Do you remember that? We did that last time. Okay, if you do that here, take the square root, and this is 8.85 times 10 to the negative 12. This is 4 pi times 10 to the negative 7. You multiply, take the square root, and you take the reciprocal. You find C equals 3 times 10 to the 8 meter per second. So you take this, and you take that, and you massage, you malax, and you shake. So do that at home, because it's just algebraic expressions. What you get at the end is that to make sure we do not do any favoritism, to make sure that half of the energy is inside the electric field, and you have a square here, and half of the energy is inside the magnetic field, and you have a square here. To make sure of that, you need to get this. Okay? So that means the magnitude of the electric field or the value of the electric field at a given time, it could be a sine wave, equals C times B. Okay, you can check, have fun at home. It's a good exercise. You need to master algebra, but that's what you're gonna get. Is that clear? So which one has the largest amplitude just in magnitude? The electric field, right? The electric field, even though they are in phase, okay, so they reach their maximum at the same time, the zero at the same time, the minimum at the same time. Nevertheless, the amplitude of the electric field is larger than the amplitude of the magnetic field. Okay, to make sure that when you plug everything, this term here will be equal to that term. Okay? It's not that hard. So usually, because remember, this is a sine wave and this is a sine wave, instead, we like to use the RMS value. Okay, so it means that the average energy density will be equals to this expression here using RMS. So both terms are equal to each other, so you can write that down. Okay, so what is it that you want to write down? Let me write it down for you. Okay, so the energy per volume, okay, average, I'm going to put a bar, average will be equals to epsilon 0 E RMS square, or it's going to be the same as V square RMS over mu 0. That's a subscript, okay? It's RMS. Okay, second of all, the E is larger than B, or E RMS is larger than. So remember that when we have a sine, remember when you have a sine function, okay, let's say it's a magnetic field as a function of time, the top here is called the peak, and the RMS you have to divide by the square root of 2, right? So B RMS, we already did that before, is peak divided by square root of 2. Remember, the peak from the outlet is 170 volt, which is square root of 2 times 120. So this is the RMS, and that's the peak. So it works exactly the same. Okay, so B is oscillating. It's going to follow a sine wave. Doesn't have to, but to approximate, we can say it's a sine wave. It's going to follow this equation, and you have that equation here. Are you with me? Any question? So I like that slide because you have. I actually, I didn't know what she was doing here when I found this slide, but now I understand, because when they do acupuncture here, you see, she's putting needle in the skin and she's using a heat lamp. Okay, so now I understand what's going on. For those who are going into physical therapy, they use also heat lamp. They use infrared. Okay, so why don't you try to do that so it will make more sense? So that comes also from Cotnell, Johnson and Cotnell. So help each other, talk to each other, blah, blah, blah. So this is the energy density, the total energy density. So this is what we call the energy density. Okay? energy density, again, it's the energy per unit volume. Okay, so if you have radiation maybe from the sun, you see radiation is flowing on its way to Earth. Okay, so I can imagine in space I'm making an invisible cube, invisible unit volume. I want to know how much energy is inside because you see radiation is flowing through that unit volume. Okay, so it's imaginary, it's a ghost volume. When I'm finding how much energy is inside. Okay, so this here would be the same as that one because we don't want favoritism. So if E is given to us, I'm going to use E, right? So the average, okay, so the energy density will be equals to epsilon 0 E RMS square, okay? Because it's the same. So I can take this one multiplied by 2. Is that clear? You sure? Okay. Okay. So that part here equals to this part. So you just multiply by 2 to get the energy. I cannot use this part because I don't know B yet. Or I could find B. I'm going to find B. So anyway, what do you get?
4.85 centimeters.
Yes. 8.5?
No, 5.8. 5.8.
5.8?
Yeah, no, 4.58.
Oh, okay. So 4.6 times 10 to the negative 6. What's the unit? Energy. What's the unit for energy? Joule. Very good. What's the unit for volume? So meter is length, meter square is area, so meter cube. Okay? Volume, a volume, like you have a cube here, 1 meter, 1 meter, 1 meter. Okay? So that's a unit volume. 1 meter per 1 meter per 1 meter. So we are talking about the energy. So you have radiation. So radiation is flowing. Remember that it takes, I think there was a question like that. I don't know if it's on the pop quiz on the homework. It takes 8 minutes for light from the sun to reach us. So it means it's moving. Okay, that means radiation is moving from the sun to us. So that means all this energy carried by the radiation is moving toward us, right? It takes time. So, okay, and find the magnetic field. And we have this equation here. So we use this equation here. So B RMS equals E RMS over C. What did you get? 2.4? Yes. Tesla. So you see that the magnetic field is smaller than the electric field because C, remember, C is a big number. It's 3 times 10 to the 8. C is 3 times 10 to the 8. Okay? Is that clear? So I'm gonna skip to, and then I will get back, but I want to skip to whatever we're gonna use for the final to make sure. Okay, so I found that picture on Amazon. I don't know. It's a heat lamp, so it's infrared. I have no idea what it's used for, but I like that because it's in all direction. Okay, it's gonna emit radiation in 3 dimensions. Do you agree with me? Okay, so I'm skipping to get to the question in the final, and then I will get back. So let's say you have a source. Okay, it could be a star. Okay, so that source, when you buy it, it will give you the power. Okay, so the power, okay, will be in watts. So what's the meaning of a power? That means joule per second. Okay, so it will be the oomph. So it means how much energy is being produced or radiate per second. Like a oomph. Okay, so the sun has power, the light bulb has power. Okay, so usually, let's say you buy it for your leopard gecko. Okay, and it says 50-watt light bulb. Okay, so that means of course it's connected here to a power supply, and that energy, it's called radiative energy. Radiative energy comes from somewhere, from electrical energy. Okay, so V times I. Okay, that energy goes into light and heat. So anyway, power is 60 watts, so it means the oomph energy produced per second. Are you with me? Pay attention, okay? Because that's going to be on the final. Wake up. Wake up. Okay, so you have radiation, but the radiation is going to spread out in 3D. Okay, so it's really in 3D, so it has to be in 3D. Do you agree? In 3D means also towards you and in the screen. So far, so good? Okay, so as if you take, for example, a small area like this, okay, 1 meter per 1 meter, do you get more radiation falling through close to the source or farther away from the source? Closer, it's going to be hotter, right? So, for example, to go back to my acupuncture, you want to make sure not to put the skin here. Of course, you're going to burn yourself. Why is that? Because the same amount of energy that you have here is going to spread out over a larger area. Copy me? Okay, so that much of energy, okay, flowing through this area, okay, will be larger than the energy here flowing through the same area. Okay? Okay, so it's actually obeying an inverse square law, which means as you move away from the source, as you move really far from the source, for the same area, so let's say you have a sensor, okay, so the sensor will have the same size, so 1 meter per 1 meter, you're going to have less energy flowing through here than through there. Do you agree? Okay, so you see here the total amount of energy per second is P. Do you agree? Okay, so now you see that same energy here. So let's see, this is your energy, total energy at a distance r. So I'm taking a distance r from the source. I'm going to call it r. This is a r. Okay, I make a sphere. It's an invisible sphere here, all around. Okay, so that same energy that you had here, okay, it's going to be there also, right? but it will spread out over a larger area. What's the area of a sphere? No. So when you have a R, it's one dimension. R squared is 2 dimension. R cubed is 3 dimension. So a sphere, is it 1 dimension or 2 dimension? A sphere, not solid, just a sphere. Like if you have a ball, okay, I agree. That will be 3 dimension. But a sphere, just the shell. No. 1 dimension, this is a 1 dimension, okay? That's 1 dimension. This is what? 2 dimension or 3 dimension? No, there is nothing here. Okay, if I do that, okay, this is 3 dimension. but this is 2 dimension, okay? Because you have a width, if you want, and a line, right? So a circle will be 2 dimensions. So it's 2 dimension. It's something that you can open with a cutter and flatten out. It's not solid. So my head is 3 dimension or 2 dimension? My head. 3. But this is 2. Because you can go this way or you can go that way. Okay, that's better. But this one is what? Which way you can go? Only one. Okay. 3 dimension, you can go this way, you can go that way, you can go there. So the area is 4 pi. So the area, it's a shell. Okay, it's an invisible shell. It's 4 pi r squared. And what's the volume that will be the volume. But that's the area. Okay, so can you find the equation? I want you to find the equation. How much energy is going to flow through just 1 meter per 1 meter, okay? How much energy, okay? So you have the energy per second. That energy is going to spread out over 4 pi r squared. Okay, so the total energy here spreading out over the whole area. It's an area because you can go this way, you can go that way. So how much energy is going to flow through that? So you want watts per meter square. What does it mean per unit area? What does it mean per? Per means you divide, okay? Okay? So let's say I'm going to call that S. Okay, that will be the energy. So what will be the energy? P, okay, per unit area. So that means I divide by the area. So 4 pi r square. Okay, so that will be the power of the source, okay, in watt. Okay, so joule watt, which is joule per second, and that will be the energy per second per area. So it means if I take a small area here that I can cut out, okay, that will be the energy flowing through it. Is that clear? So that unit here will be watt per meter square. Okay? Let me show you. So that's the thing you have to understand before the final, but I have a very nice picture here. You see, this is your power, right? 60 watts. That's the oomph. The energy here is going to spread out in 3 dimensions. So that same energy here will spread out over the whole area, okay, the whole sphere here. Okay, so how much energy I'm gonna get here? It will be power less, okay, divided by 4 pi r squared, okay, because you divide by the area of the sphere. It's actually, we already did that in the physics 1, it's inverse square law. Do you see? And I think there is one question for the homework like this, right? So let's say it goes like that, but then I will go back to my, so let's say you have a butter gun. You know, you see you have those guns you can spray butter with for the lazy people. And plus it's not healthy, it's very processed. But it's just for the sake, oh, you can do a demo with that, okay? So you have your gun here, you have your French toast, and ooh, you have a very, very thick layer of butter here. Very, very thick, right? Like this. And you say, oh, that's not healthy, okay? So now you multiply the distance by 2, okay? You multiply distance by 2, so the same amount of butter will spread out over, yes, 4 times the area. Multiplied by 2, the area will be multiplied by 4. So how many French toast you can spray? 4. Make sense? If you multiply by 3, you still have the same amount of butter, okay, available. You spray during the same time, but now you see the thickness here will be divided by 9, okay? And then you can feed more people because you have 9 French toast, okay? Don't buy those stuff. Buy the Irish butter. It's much better. Yes, Kerrygold is good. Or the one from there is Irish and the other one is I forgot. But don't buy those fake butter. Margarine, it's very bad. Margarine is very bad. There is a whole story about that. It was a byproduct they try to recycle and they make people think that it's healthy, but it's a killer. Okay, margarine is a killer. It's very unhealthy. So let's take an example. Okay. So you have the power. And the power is 60 watts. So you buy that lamp here for your gecko. How much you're gonna get at a distance R equals 30 centimeters, for example. So how much watt per square meters? Okay, so this is watts, so just joules per second, and I want watt per square meter at a distance of 30 centimeters. So then I will feel better for the finals. Okay, you are at a distance here. It's supposed to be a sphere. Okay, so it will be the same amount of energy flowing. It's flowing through the sphere. And now I take one small square area, 1 meter per 1 meter, small area here, and I want to know how much energy is flowing through it. Okay, so that will be watt per meter square. Okay, so you can do P, that will be the source, divided by 4 pi r square equals S. So that will be in watts per meter square that will be in meter square. Another trick when you are taking exam, for example, check the units. Make sure it makes sense. If this is watt, this is meter per second, that will be watt per meter per second. So you are using this equation here. So that means energy per unit area. When you divide, that means per unit something. Okay, so if you have a speed, distance over time, that means per unit time. For a time equals to 1 second. Area equals 1 meter square. So what do you get? 53. So 4 pi. And then here, did you square it? Okay. 53. 53 what?
Wait, 0.
But the unit watt per meter square. Okay? You see how it works? And everyone, it makes sense? So when you say per unit something, it means you divide. So for example, we have our sun. So this is the sun here. And okay, so the sun is radiating. So I have radiation, flowing, so energy. Okay. By the time it gets to the earth, so here you have the earth. Okay. So you see on the earth, you can make a small square here on the earth, like a solar panel, 1 meter per 1 meter, and you can find out how much radiation do I get from the sun. And the sun is a white bulb, a super light bulb with a power of, I think it's something like this, 4 times 26 watts. That's our sun. And the distance between Earth and the sun, I think it's 150, I think it's million kilometer. So you have to convert million and you have to convert kilometer. So here on Earth, I have a solar panel that I put on my house. Let's say I don't have a house, but let's say I have. So I have a solar panel 1 meter per 1 meter, and I want to know how much energy do I get. Okay, so then I can find out, what is it that I can power in my house, for example. Okay, so try to do it. I'm going to check the distance between Earth and the Sun. Is that correct? What about the power of the Sun? Is it something 10 to the 26? 3.3? Oh, okay, so we're good. Okay, so do it. So S will be watt per square meters equals P over 4 pi distance square. So it's a good review of scientific notation, 4 pi. So you have to put that in meter. So million is 1, 2, 3, 4, 5, 6. Kilometer is another 1, 2, 3. Kilometer is 1, 2, 3. So 6, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Is that right? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. So what did you get? Hmm.
Square 12 times 10 to the 14.
14. 14. So something is wrong. Okay, either it's something. Let's see. 4 times 10. Okay. Ah, 1,000. Yes, yes, yes. 1,000. Huh?
Billion instead of million.
No, 1,000. Billion. 9 10. Are we doing it? 4 pi r square. Yeah, there is no 10 to the 14. Why is there a 10 to the 14?
I forgot.
Okay, so make sure you square. So 4 times 10 to the 26. Okay. Divide by 4. Okay. Divide by pi. Where is my pi? Okay. Divide by 1.5 times 10 to the 11. That you square. Okay, you see how to do it? You have to go step by step. Divide by this, enter, divide by that, enter, divide by, open the parentheses, blah, 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 square. And blah, blah, blah has to be 10 to the 11 because million is 1, 2, 3, 4, 5, 6. Kilometer is 1, 2, 3. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Okay? It's a nice review for scientific notation. You see, it's not physics that kills, it's the math. So don't blame me. That's scientific notation, right? So did you all get that now?
Yeah.
Okay, it's about something like that. So how do I get from the sun? Listen, not much. Yes.
So 1.5 to times 10 to the negative 11.
Not negative, 11. 1.5 times 10 to the 11.
That
Yeah, but 150 million kilometer. Okay, so 150. Huh? Oh, no, million. Oh, it's billion. Okay, this is billion. Okay, you can say this is billion. So 1, 2, 3, 4, 5, 6, 7, 8, 9. So 150 times 10 to the 9.
No, because what happened is that she has a 150 million kilometers, but the one that we saw online was in meters, so they're equivalent to each other.
Hi? Oh, the one I saw online. That's what you're telling me. Yeah, so it will be the same thing because here you have 9 zeros. Okay, billion is 9 zeros. And here you have 9 0. 1, 2, 3, 4, 5, 6, 7, 8, 9. Kilo is 3 zeros, right? So you can say
Just meters. Hence why I took it in the other things already. Exactly.
so 150 million kilometers. So you can say billion meters or million kilometers. Okay? So how much is 1 meter per 1 meter? Okay, it's about this. You see this? Okay, little bit larger than that. that. Okay, you take that outside and you have to go to the equator. Okay, to the equator. So the sun goes straight perpendicular to that. You will only get 1000 watts. 1000 watts is nothing. Okay, so it's good for little appliances, but you cannot power a whole house, and it's difficult. Otherwise, you have to cover the roof with solar panel. So this is just in case, okay, when the solar panel is perpendicular to the rays. If the solar panel is like this, or the rays are like that, it's not going to collect the same amount. And of course, it has to be sunny. If it's cloudy, forget it. So it's good, it's nice, can power a small house, but a whole city, I don't think so. Okay? Is that clear? So if you take an astronomy class, for example, instead of calling P, they call that. So for example, you have a star here, okay, and it's gonna radiate energy in 3 dimensions. The power of a star is called its luminosity. So it will be the oomph. And then at a given time, if you have 1 meter by 1 meter, okay, it's going to flow through it. That will be called, what you get here will be called the brightness. So we have this equation. The brightness will be equals to the luminosity divided by 4 pi distance square. Okay, so that will be the distance. So why is it a big deal? Because if you collect the light from a star and we know its luminosity, what is it that you can figure out? Okay, if you have the brightness, okay, so you look at a star, you look how bright it appears to be, and you know its real oomph, so how bright it's really. What is it that you can find? The distance. That's how we find the distance to galaxies, for example, very far away. We look at supernovae. We know how bright the supernovae is supposed to be. We look at how bright they appears to be. So we can find the distance to very, very far away galaxies just after the Big Bang. And that's how we know that the universe not only is expanding, but accelerating. So it's moving, it's expanding faster now that it used to be expanding back then. We don't know why. Okay, any question? Okay, so if I give you that for the final, you will know how to use this equation. It's also called the inverse square law. Okay, you multiply the distance by 3. Okay, the amount of light that you get here will be divided by 9. It works for radioisotopes, like radioactive stuff that you use in medicine, for example. If you move away from your radioactive source, okay, if the distance from the radioactive source is multiplied by 3, the amount of radiation that you get, okay, for a unit area will be divided by 9. Okay, so radioactivity goes down very quickly as you move away from the source. It works the same for gravity, electric field as well. Okay? So that says, they call that vector here, that physical quantity S. Okay, so that means power per unit square. They call it in your book the poynting vector. Poynting because it's named after someone named Henry Poynting. So it's the name of a physicist. Okay, so it will be, if you imagine an area here, you see the radiation is flowing through this area, and you can define how much energy per unit area is flowing through it. Okay? So here, you can do that at home. It's a little bit more advanced. You can pull a little bit of hair and you will find the answer. You have the answer. Okay? The other thing I wanted to show you. So there is a big thing about light therapy. So I guess it's not for us, but for people who live up in the north, you see people tend to be depressed because they need infrared, okay? They need red light, actually. There is a study that shows that since you are in biology or medicine, we need infrared to repair the mitochondria of the cells, right? So we need red light and we need infrared. So anyway, my point that is that when you buy red light for light therapy, you see they do the computation for you. See, you can see that if you are at that distance for an area equals to what here? What's the area? Is it meter? Centimeter square, right? So what does it mean? You take a small square, okay, 1 centimeter by 1 centimeter, okay, how much energy per second is going to flow through this area? So M means what? Milliwatt. So 10 times 10 to the negative 3 watt per square meters. Okay, so now you can translate that. You understand what it means? You see that if you are closer from the source, okay, they did the computation and now you get 200 milliwatt per square meters. So it's not going to be an inverse square law because why do you think it's not an inverse square law? Is the light spreading in 3 dimensions? No, okay? It's not the same. If you have a light bulb like this, it doesn't go in 3 dimensions. So the computation won't be exactly the same, okay? Because it doesn't spread out over a sphere. Does it make sense? And red light. We are lucky here. We don't need that. You can also see here. So here, it's not over an area, okay? It's just over this distance here. And if I look at the amplitude, you see, as you move away from the source, can you see that the amplitude is decreasing, right? Because the same energy that you had here, which is inside the amplitude of the wave, is going to spread out over a larger distance. Does it make sense? So here you're going to have very big crest, and as you move away from the source, okay, that energy is going to spread out over that distance here, that circle, so the amplitude is going to decrease. So in that case, it will be 1 over r, because it's not in 3D. Isn't that interesting? You say, yes, it's interesting. So next week, you can relax, okay? No more math. It will be just conceptual questions. I have uploaded the practice exam, okay? So if you want, and I have an assignment. And today we have a pop quiz.
We have practices for next week.
A pop quiz also next week.